In episode 21, titled Distribution Families, Normal, Uniform, Binomial, Poisson, and T-Distribution, the goal is to identify distributions fast so you can choose correct methods without guessing, because DataX questions often hide distribution clues inside scenario language. You are rarely asked to label a distribution for its own sake. You are asked to choose a test, an interval, an interpretation, or a modeling approach, and those choices depend on the data-generating process. When you can recognize the shape and the process that produced the data, you can pick methods that fit the conditions rather than forcing a convenient assumption. This matters because many distractors rely on learners defaulting to the normal distribution even when the scenario clearly implies counts, bounded ranges, or rare events. In this episode, we will cover the normal, uniform, binomial, Poisson, and T-distribution at the level the exam expects, focusing on what they represent and how you recognize them quickly. By the end, you should be able to hear a scenario and immediately suspect the right family, which speeds up both method selection and interpretation. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The normal distribution is the most familiar, and it is best described as symmetric around its mean with relatively thin tails compared to heavy-tailed alternatives. Symmetry means values above and below the mean occur in a balanced way, and many natural measurement processes with many small independent influences can produce approximately normal behavior. Thin tails means extremely large deviations from the mean are relatively rare compared to distributions with heavier tails, which matters when you are deciding how likely extreme values are. The exam may describe measurements like manufactured part dimensions, repeated sensor readings under stable conditions, or aggregated metrics where central limit theorem intuition applies, and those are places where normal thinking can be reasonable. The normal distribution is often summarized by parameters like mean and variance, which set the center and spread, and that parameter simplicity is part of why it is widely used. However, the exam also expects you to avoid treating normal as a default when the scenario suggests bounded values, counts, or strong skew. When you keep normal as symmetric thin-tailed measurement behavior, you will recognize when it fits and when it does not. The uniform distribution is conceptually simpler, and it describes equal likelihood across a bounded range, meaning every value in the range is equally likely. This is a good model for situations where a process produces outcomes with no preference inside fixed limits, such as a randomized selection that is designed to be fair, or a timing process that is equally likely to land anywhere in a defined window. The key cues are boundedness and flatness, because a uniform distribution has a clear minimum and maximum and no concentration around a central value. The exam may describe a random number generator, random assignment to a range, or a scenario where all options are equally likely by design and uniform becomes the plausible model. Uniform is not common for many natural measurements because real processes often cluster, but it appears in exam contexts because it is a clean conceptual contrast to normal. Recognizing uniform prevents you from incorrectly applying bell curve thinking to something that is intentionally flat. When you see bounded range and equal chance, uniform should be on your short list. The binomial distribution describes the count of successes across a fixed number of trials, where each trial has two outcomes and a consistent probability of success.
This is the distribution behind questions like how many clicks out of this many impressions, how many defects out of this many items, or how many customers churned out of this group, when the trials are treated as independent and similarly distributed. The key cues are a fixed number of trials, a yes or no outcome, and a probability of success that is stable across trials, at least as a modeling assumption. The binomial has parameters that include the number of trials and the success probability, which are often implied by scenario language rather than stated directly. The exam likes binomial reasoning because it connects naturally to proportions, conversion rates, and classification evaluation, which are common topics. It also links to confidence intervals and hypothesis tests for proportions, because those are built on binomial and related approximations. When you hear count of successes out of a fixed number, binomial thinking should come quickly.
The Poisson distribution is used for counts across time or space when events occur at some average rate, particularly when events are rare and independent within small intervals. The key idea is modeling the number of arrivals, incidents, or occurrences in a fixed window, like calls per hour, failures per day, or anomalies per minute. Poisson is often connected to the idea of a rate, which is a parameter representing the expected count per unit time or space, and that rate is what controls the distribution's center. The exam may describe arrivals, incidents, or events that happen sporadically, and those are strong Poisson cues, especially when the question focuses on a time window rather than a fixed number of trials. A useful contrast is that binomial assumes a fixed number of opportunities with success or failure, while Poisson assumes a flow of events over time with an average rate. Poisson is also used as an approximation to binomial in certain rare event conditions, but the exam usually tests the conceptual difference rather than that approximation detail. When you see events per interval, Poisson should be the distribution you suspect. The t-distribution matters because it behaves like a normal distribution but with heavier tails, especially when sample sizes are small and you are estimating variability from the data. Heavier tails mean it assigns more probability to extreme values than the normal distribution does, which makes it more cautious and more realistic when uncertainty about the standard deviation is high. The exam often introduces this through mean comparisons and confidence intervals with small samples, where t-based methods are preferred over normal-based methods because they account for additional uncertainty. The key cue is small sample size combined with mean inference, because that is where the t-distribution becomes the natural tool. As sample size increases, the t-distribution approaches the normal distribution, which means the distinction matters most early and fades later. The t-distribution is also connected to t-tests, which you have already discussed as mean comparison tools, and this family linkage often appears in test selection questions. When you see small samples and mean inference, t-distribution thinking becomes an exam-relevant signal. The fastest way to choose among these distributions is to focus on data-generating process clues rather than on surface-level labels. If the data is a measurement influenced by many small factors and appears symmetric, normal might fit as an approximation. If values are evenly spread within clear bounds by design, uniform is a plausible model. If you are counting successes out of a fixed number of independent trials, binomial is a natural choice. If you are counting events arriving in time or space with an average rate and no fixed number of trials, Poisson often fits. If you are doing mean inference with small samples and uncertain variance, the t-distribution becomes relevant. The exam rewards process-based selection because it prevents you from matching names by habit and encourages you to choose methods that fit the scenario structure. When you practice reading scenarios as what process created these outcomes, your distribution choices become more consistent and less stressful. Parameters are the language of distributions, and recognizing which parameters matter helps you interpret scenarios quickly. Normal behavior is often described by mean and variance, which describe center and spread, and scenario language about average and variability often points here. Uniform behavior is described by its lower and upper bounds, and scenario language about within a range and equally likely points here. Binomial behavior is described by the number of trials and success probability, which connects to counts, rates, and conversion thinking. Poisson behavior is described by a rate, which is the expected number of events per unit time or space, and scenario language about incident rates points here. The t-distribution is tied to degrees of freedom, which you do not need to compute for the exam in most cases, but you should recognize it as a small sample correction to normal-based inference. Understanding parameters also helps you recognize when a scenario is missing information, because some questions test whether you know what you would need to specify a model. DataX rewards parameter awareness because it shows you are thinking about what defines the distribution, not just what it is called. Practice becomes easier when you match scenarios like arrivals, defects, clicks, and durations to the distribution families in a consistent way. Arrivals and incidents per time window are common Poisson cues, especially when you are given a rate and asked about counts in a window. Defects out of a fixed batch are common binomial cues because each item is a trial with defect or no defect. Clicks out of impressions are also common binomial cues because each impression is a trial and click is a success, though dependence and selection can complicate reality. Durations can be tricky because many duration processes are skewed rather than normal, which is why the exam may use duration scenarios to test whether you avoid forcing normal assumptions. Uniform can appear in scenarios about randomized assignment or timing uniformly distributed within a window, while normal often appears in contexts where measurement noise is symmetric. The t-distribution often appears behind the scenes when the scenario involves small sample mean inference, even if the distribution of raw data is not stated. When you build a mental library of these matches, you can move quickly from scenario to method. A frequent exam error is forcing normal assumptions on strongly skewed behavior, and distribution recognition helps you avoid that trap. Many real-world variables are bounded, count-based, or heavy-tailed, meaning they do not behave like a symmetric bell curve. Transaction amounts, response times, and event counts often have long right tails, where a few extreme values dominate the mean and break normal intuition. The exam may describe extreme spikes, rare high values, or a strong right skew, and those are signals to be cautious about normal-based summaries and tests. In those cases, the best answer often involves using robust methods, transformations, or distribution families that better match counts and rates. DataX rewards this caution because it reflects experienced practice, where method choice follows data behavior rather than convenience. When you resist normal default thinking, you reduce the chance of choosing a wrong test or a misleading interval. Distribution choice connects directly to test selection and interval estimation because different families support different inferential tools and different assumptions. Mean comparison tests often rely on normal or t-distribution logic, depending on sample size and variance uncertainty. Proportion and count questions often rely on binomial or Poisson logic or on approximations derived from those families. If you choose the wrong distribution family, you may choose a test that is inappropriate or interpret a confidence interval incorrectly. The exam often asks you to pick a method, and the correct method implicitly assumes a distribution family that matches the data type and process. This is why distribution literacy improves performance across many topics, because it gives you an upstream sorting mechanism before you choose a downstream tool. DataX rewards learners who can connect "what kind of data is this" to "what methods are appropriate," because that is the practical workflow of analysis. When you treat distribution identification as the first step in method selection, your answers become more reliable. When the distribution fit is poor, the exam expects you to know that you can use transformations or non-parametric approaches rather than forcing an inappropriate model. Transformations can help make skewed data more symmetric or stabilize variance, which can make normal-based methods more defensible in some contexts. Non-parametric methods reduce reliance on strict distribution assumptions, which can be useful when the data is clearly non-normal or when sample sizes are small and outliers are influential. The exam does not usually ask you to execute transformations, but it does ask you to choose an approach that respects the data behavior described. A common distractor is a method that assumes normality even when the prompt highlights strong skew, heavy tails, or outliers, and the correct answer often involves robust choices. DataX rewards this because it shows you understand that model assumptions are conditions, not decorations. When you can say that poor fit should lead to transformation or non-parametric alternatives, you are applying distribution thinking in a practical way. A reliable memory anchor is that shape and process guide distribution choice because it keeps your attention on what matters in scenario recognition. Shape refers to symmetry, tails, boundedness, and whether values are counts or continuous measurements, while process refers to fixed trials, event arrivals, or measurement noise. When you hold both, you can quickly decide whether you are dealing with a mean-centered measurement, a bounded flat range, a fixed trial success count, a rate-based arrival count, or a small sample inference situation that needs heavier tails. Under exam pressure, this anchor prevents you from choosing distributions by name familiarity and pushes you toward defensible reasoning from scenario cues. It also sets you up to choose the right test, interval, or model family downstream, because those choices depend on the distribution family you are implicitly assuming. DataX rewards this anchor-driven reasoning because it is consistent and replicable across many question types. When you use shape and process together, your answers become faster and more accurate. To conclude episode 21, match 3 scenarios to distributions and then explain why, because explaining the why locks in the process cues that the exam is testing. Choose one scenario that involves a numeric measurement with symmetric noise, one that involves successes out of fixed trials, and one that involves event arrivals in a time window, and then name normal, binomial, and Poisson as appropriate. Then add the caution that small samples in mean inference point toward the t-distribution rather than normal, and that uniform applies when outcomes are equally likely within strict bounds. Finally, state that strongly skewed behavior should not be forced into normal assumptions, and that transformations or non-parametric methods may be more appropriate when fit is poor. When you can make those matches quickly and justify them in plain language, you will handle DataX distribution questions with calm confidence and method-aware judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.